Tonight, we're going to explore one of the most stubborn mysteries in planetary science. Venus is often called Earth's twin. It's almost the same size, nearly the same mass, and formed from the same cloud of gas and dust around 4.5 billion years ago. By every prediction, it should have evolved much like our own planet, but it didn't. Venus spins in the opposite direction. Not only that, it spins so slowly that a single day on Venus lasts 243 Earth days, longer than the planet takes to orbit the Sun. Its axis is tilted by nearly 177 degrees, leaving it almost completely upside down compared to most of the solar system. 7 planets rotate in one direction. Venus alone spins the other. After more than 60 years of research, scientists still can't fully explain why. Every leading theory explains part of the mystery, yet each leaves behind questions it can't answer. And to make matters worse, Venus has erased much of the evidence that could reveal what really happened billions of years ago. By the end of tonight, you'll understand why Venus rotates once every 243 Earth days instead of every few hours, why its backward spin challenges our understanding of how planets form, and why the answer may have disappeared beneath the planet's surface billions of years ago. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Look closer at the 2 planets, and the resemblance only deepens. They formed in the same narrow ring of the early solar system's inner disk, from the same metal fragments and the same volatile pore silicates, in the same proportions of rock and iron. Venus's mass is about 81.5% of Earth's. Its radius is about 95%. Its density is nearly identical, and its core composition matches. If you could take a sample of material from both planets at the moment of their formation and hand them to a chemist, she could not tell them apart. That matters, because in planetary science the rule is clear. You inherit your spin from the cloud that made you. When a vast cloud of gas and dust collapses under gravity to form a solar system, it carries a slight rotation with it. That rotation gets preserved, transferred down to every planet that forms from the disk, like a whisper passed from a parent to a child. The technical term is angular momentum conservation, but the plain meaning is simpler. Formation physics is deterministic. Planets spin the way they do because the cloud spun that way first. And every planet in our solar system should spin in the same direction, because every planet came from the same cloud. 6 of them do. Earth rotates counterclockwise when viewed from above the solar system's north pole. So does Mars. So do Jupiter, Saturn, and Neptune. Mercury as well. 7 of the 8 planets in our solar system rotate in this prograde direction, the direction their shared formation cloud was already turning. Venus does not. Venus rotates clockwise. Viewed from above, while every other planet turns counterclockwise, Venus turns the opposite way. Its rotation runs backward relative to its orbit. This is not a slight tilt or an offset. This is a full reversal. The rotation of the planet is moving in the exact opposite direction of the way it moves around the Sun. The consequence is concrete and strange. If you stood on the surface of Venus and watched the sky long enough, the Sun would rise in the west and set in the east. Every morning would run backward relative to every morning on Earth. What formation physics predicts with confidence, Venus simply ignores. This is what planetary scientists call a first-order rule violation, not a minor discrepancy in a secondary measurement, not an edge case where the models come close. The most fundamental prediction we can make about a planet's spin, that it will match the direction of the cloud that formed it, is simply wrong. Venus has overwritten that initial condition completely. And the question the rest of this script will pursue is what exactly did the overwriting? But the direction reversal is only the first anomaly. Let's think about speed. Planets spin, some faster, some slower. Earth completes one rotation in roughly 24 hours. Jupiter, despite being a gas giant over 1,000 times Earth's volume, spins so fast, it completes a full rotation in just under 10 hours. Even Mercury, the smallest planet in the solar system, rotates once every 59 Earth days. These are all wildly different speeds, but they all exist within a reasonable range for what formation physics produces. Venus takes 243 Earth days to complete a single rotation. Think about what that means. Not 243 hours, not 243 minutes, 243 Earth days to turn once. A single Venusian day lasts longer than most planets take to complete multiple full orbits. Venus rotates so slowly it has nearly stopped. It is spinning in the wrong direction, and it is barely spinning at all. But here's where it gets strange. Venus completes its full orbit around the Sun, its Venusian year, in 224 Earth days. The orbit is 224 days. The rotation is 243. The day is longer than the year. Venus rotates so slowly that it finishes its trip around the Sun before it finishes a single turn on its own axis. Imagine trying to keep a calendar on that world. You would complete one full trip around the Sun before you would live through even one local sunrise to sunrise cycle. The fundamental rhythm of time that every other planet organizes its existence around simply does not hold on Venus. Not a slight distortion. A complete collapse of the expected relationship between day and year. Now consider the third anomaly. Tilt. Earth's axis is tilted at 23.5 degrees relative to its orbital plane. That tilt is why we have seasons. It is a modest, reasonable number. Mars is tilted at about 25 degrees, Saturn about 27. Even Uranus, often cited as the solar system's great oddity because it appears to be rolling on its side, has an axial tilt of about 98 degrees. It is dramatically tilted, tipped sideways, but not inverted. Venus has an axial tilt of 177 degrees. Earth's tilt is 23.5 degrees. Uranus is about 98 degrees. Venus is 177 degrees. That is 3 degrees short of a perfect 180-degree flip, 3 degrees away from being precisely and completely upside down. This is where an interpretive split opens up, and it runs deep enough to matter. Two framings of Venus's tilt are both geometrically consistent with what we observe. In the first framing, Venus tilted almost 180 degrees from its original orientation while still rotating in its original prograde direction. In the second framing, Venus genuinely reversed its rotation while keeping its axial tilt relatively small. Mathematically, these two descriptions produce the same observable result. A planet tilted 177 degrees rotating prograde looks identical from the outside to a planet tilted slightly rotating retrograde. The appearance is the same, the history is not. And distinguishing between those two histories, understanding whether Venus slowly tipped over or slowly spun backward, is one of the core unresolved questions surrounding this planet. What we can say clearly is this: Venus is doing three things simultaneously that no other planet in the solar system is doing. It is spinning in the wrong direction. It is spinning at almost zero speed, and its axis is almost completely inverted. Any one of these would be unusual. Together they form a picture of a planet whose entire rotational identity has been transformed. Whatever Venus was at formation, it is not that anymore. Of the 8 planets orbiting our Sun, 7 remember the direction of the cloud that built them. Venus has forgotten, or something made it forget. Spin is supposed to be a planet's deepest memory, the one record of its origins that nothing should be able to erase. Venus's memory has been rewritten, and that rewriting is what every theory we will examine tonight has tried, and so far failed, to fully explain. The direction is wrong, the speed is wrong, the tilt is wrong. 3 anomalies locked together in the same planet, and none of them, taken individually, point clearly to a cause. But taken together, they point to something significant enough and strange enough to have driven 6 decades of competing theories, none of which has yet won. That was only the first layer of the problem. To see what was overwritten, you first have to understand what every planet should have inherited. About 4.5 billion years ago, there was no solar system. There was a cloud, an enormous, diffuse cloud of gas and dust, mostly hydrogen and helium, with traces of heavier elements forged in the cores of earlier stars and scattered by their deaths. That cloud was not perfectly still. Nothing in space is perfectly still. It had a slow drift, a faint rotation, almost imperceptible. Then something disturbed it. a shockwave from a nearby supernova, or an instability in the cloud itself. The cause is uncertain. What followed is not. Gravity took over. The cloud began to collapse inward, and as it collapsed, something happened that would determine the shape of every object that followed. Angular momentum, the tendency of a spinning object to keep spinning and to spin faster as it shrinks, was conserved. Think of a figure skater pulling their arms in toward their chest during a spin. They do not change their total rotation. They concentrate it. The cloud did the same thing. As it collapsed from an enormous diffuse sphere into something smaller and denser, its slow drift became a faster rotation. The cloud began to flatten. A sphere has no preferred plane. A spinning, collapsing cloud does. It flattened into a disk, the way a ball of pizza dough flattens when you spin it. Hydrogen piled at the center, grew dense and hot, and ignited nuclear fusion. That was the sun. The rest of the disk was not empty. Fine dust particles collided gently and stuck. Pebbles formed, then boulders, then bodies large enough to pull other material in with their own gravity. Scientists call these planetesimals, the raw building blocks. The planetesimals kept colliding and merging. The mergers built Mars-sized bodies called protoplanets. The protoplanets kept accumulating. After tens of millions of years, 8 planets remained. Here is the point that matters. Every single collision, every single merger happened inside the rotating disk. The disk had one direction of rotation. The material building the planets was already moving in that direction. When pieces merged, they merged within that flow. The result was that merged bodies kept rotating in the disk's direction. Not because anything special happened, because nothing special happened. Prograde rotation, spinning in the same direction as the disk, is simply what you get when the process runs undisturbed. This is why the solar system looks the way it does. The sun rotates prograde. The planets orbit prograde. Most moons orbit prograde. Most planetary rotations are prograde. The asteroid belt moves prograde. The Kuiper belt moves prograde. All of it is a fingerprint of the original cloud. The direction was baked in from the first moment of collapse, reinforced by every subsequent collision, preserved across billions of years. Prograde is not interesting. Prograde is the default. Retrograde requires a story. We see retrograde objects in the solar system. Triton, the largest moon of Neptune, orbits its planet backward. But Triton has a story. It is almost certainly a captured Kuiper belt object, a body that formed elsewhere in the outer solar system and was dragged in by Neptune's gravity. It did not form where it is. Its retrograde orbit is the signature of its foreign origin. Capture is a known mechanism. It is not common, but it is understood. Venus does not have that story available to it. Venus is the second planet from the Sun. It is large, nearly Earth-sized, built from the same rocky, iron-rich material as Earth, Mercury, and Mars. It has the composition of the inner solar system. It has the mass of a world that formed in the inner solar system. A planet cannot drift in from the outer reaches of the disk and park itself this close to the Sun with this kind of composition. The physics does not allow it. Venus formed where it is. Whatever rotation it has now, it earned here inside the original disk, in the prograde frame. And yet it rotates retrograde. That means something changed Venus after formation. Not a small change, not a nudge. A planet's spin is its most stable property. Orbits can be disturbed by gravitational interactions with other bodies over long timescales. But spin is different. Spin is the record a planet keeps of how it was assembled. It takes catastrophic, sustained, or extraordinarily unusual conditions to change it. To reverse a spin entirely, to take a planet rotating one way and force it to rotate the other way, requires energy on a scale almost impossible to imagine. Not a single, ordinary impact. Not a passing gravitational tug. Something of enormous consequence. Whatever that something was, we did not know it had happened for most of human history. Because for most of human history, we could not measure Venus's rotation at all. Venus is wrapped in permanent cloud cover. Not thin, wispy clouds you can see through. Thick, continuous, planet-wide sulfuric acid clouds, layered tens of kilometers deep, sitting atop a haze that extends even higher. These clouds reflect almost all of the sunlight that hits them. That is why Venus is the brightest object in the night sky after the moon. It is not glowing. It is a mirror, but that mirror hides everything beneath it. Through an optical telescope, Venus is a featureless, creamy sphere. No surface markings, no polar caps, no visible rotation. You could watch it for decades and see nothing move. Before the 1960s, guesses about Venus's rotation period covered an enormous range. Some researchers thought it might be tidally locked, meaning its rotation period exactly matched its orbital period, always showing the same face to the Sun, the way our moon always shows the same face to Earth. Others thought it might rotate roughly every 24 hours, similar to Earth. Some proposed something in between. There was no consensus. There was no data. The cloud cover made every estimate a guess. Then, in 1961 and 1962, radar astronomers changed that. The technique was not simple, but the principle was this. Radio waves travel through clouds without scattering, the way visible light cannot. A radar telescope can aim a powerful pulse of radio energy at a planet, and that pulse will pass through the cloud layers, bounce off the solid surface, and return. By analyzing the frequency shifts in the returned signal, how some parts of the returned echo are shifted slightly higher in frequency and others slightly lower, astronomers can measure rotation. A surface rotating toward the receiver sends back waves bunched slightly closer together, shifted upward in frequency. A surface rotating away spreads them slightly farther apart, shifted down. The same principle used in police radar to detect a car's speed, applied across a distance of tens of millions of kilometers. Using Arecibo in Puerto Rico and Goldstone in California, Roland Goldstein and others directed those radio pulses at Venus. They collected the echoes, they analyzed the frequency shifts and the time delays, and what came back matched nothing on the list of predictions. The rotation period was approximately 243 Earth days, not 24 hours, not tidally locked in 1 year. 243 Earth days to complete a single rotation, slower than anyone had seriously proposed, barely turning at all, and the direction was wrong, completely wrong. The rotation was retrograde, against the grain of the entire solar system. The result was refined and confirmed over the following years. By the mid-1960s, the measurement was firm, approximately 243 Earth days. Axial tilt, approximately 177 degrees. Retrograde, against every expectation the standard formation model could offer. In 1965, Roland Goldstein and R.L. Carpenter published their analysis. Their framing was careful. The only limit on explanations for Venus's retrograde rotation, they wrote, was the imagination of the theorists. It was a polite sentence. What it meant was simpler. No one knew. The observation had broken the framework. The framework could not simply be adjusted. Something had to be invented from scratch to account for a planet that should have been prograde, was built inside a prograde disk, formed in a prograde system, and yet spun the other way. The first instinct was an impact. Something had hit Venus, something enormous, and the collision had flipped it. It was the simplest story, but simple is not the same as correct, and the decades that followed would show just how difficult it is to tell this particular story without it falling apart. The search for the real explanation was only beginning. Before asking what hit Venus, it is worth asking something harder. Why should a planet's spin be so difficult to change at all? And why does backward turn out to mean something less certain than it sounds? Spin is not arbitrary. It is a record. Every rotating object in the universe carries what physicists call angular momentum, a conserved quantity that combines mass, how that mass is distributed, and how fast the object is turning. It is the same property that explains why galaxies flatten into disks instead of staying as spheres, why planets orbit instead of falling straight in, why a figure skater who pulls her arms inward turns faster without anyone pushing her. The angular momentum was already there. The shape change just redistributed it. The key word is conserved. Without an external force twisting the system, angular momentum does not leak away. It does not decay. It does not erode with time. A planet formed from a spinning disk inherits the angular momentum of that disk. And unless something outside the planet acts on it, that angular momentum stays locked in, essentially forever. This is why most planets are well behaved. Mercury was nudged by solar tides over billions of years, into what astronomers call a 3-to-2 spin-orbit resonance. That means Mercury completes 3 full rotations for every 2 orbits around the Sun. Not a perfect lock, but a tidy, stable pattern that gravity settled it into. The mechanism is understood. Earth has been slowing down gradually, pulled by the Moon's tidal friction. That process is measured, predictable, and gentle. Mars rotates at almost exactly Earth's rate. Not because Mars and Earth are twins, but because nothing significant has happened to Mars's rotation since it formed. The angular momentum it inherited from the early solar system is still there, largely untouched. These are planets whose spin reflects their origin. The imprint of the ancient nebula is still visible in how they turn. Then, there is Venus. Venus's current rotation cannot be its original rotation. The physics make that clear. The angular momentum Venus carries today is dramatically different from what any reasonable formation model predicts. Something altered it, not nudged it, not shifted it slightly at the margins, substantially changed it. 2 broad categories of mechanism could have done this. The first is a single violent event, an impact large enough, a collision catastrophic enough to transfer angular momentum quickly and decisively in a single episode. The second is something slower. Sustained torques acting over geologic time, through atmospheric tides, gravitational coupling, or interactions that accumulated effect across hundreds of millions of years. Both categories are physically plausible. Both can produce, in principle, something like what we see now. The observations alone cannot choose between them. To choose, you need secondary evidence. Clues preserved in the planet itself. Isotope ratios in the atmosphere, gravity field anomalies, surface age patterns. Anything that still carries a memory of the earlier state. But something was wrong. Venus has almost no memory left to read. About 500 million years ago, Venus's surface was resurfaced. The entire crust, as far as we can tell, was repaved by volcanic activity. Whether this happened all at once in a single catastrophic event or accumulated steadily over time is itself uncertain. But the result is the same. Whatever geological record existed before that point is gone. No ancient crust survives. No primordial terrain. Compare that to Earth. Earth still preserves zircon mineral grains nearly 4.5 billion years old. Nearly as old as the planet itself. Those grains are tiny time capsules, carrying chemical signatures from the early solar system. Geologists can read them. They can trace the history of a world that has been geologically active for billions of years, and still kept fragments of its beginning. Venus kept nothing. The task of reconstructing what happened to Venus's rotation is something like arriving at the end of a Rube Goldberg machine, watching the final marble roll to a stop, and being asked to deduce the exact setup that produced it. Every chain in the middle has been removed. Only the result remains. And the result is consistent with more than one chain. That ambiguity runs even deeper than it might seem. Because the question is not only what changed Venus's spin, the question is what backward actually means. Rotation direction is not an absolute. It is defined relative to a reference frame. The one astronomers use for the solar system is the orbital plane as seen from above the Sun's north pole. From that vantage, every planet orbits counterclockwise. The Sun itself rotates counterclockwise. The vast majority of moons, asteroids, and Kuiper belt objects follow the same sense of rotation. Venus, from that same vantage, rotates clockwise. Its rotation axis points nearly opposite to the solar system's rotation axis. It is close to perfectly inverted. Now here is what the geometry allows. There are 2 physically distinct ways to arrive at this configuration. The first, Venus's rotation genuinely reversed. It was once prograde, spinning counterclockwise, and over time it slowed, passed through zero, and continued into the negative, spinning clockwise instead. A true reversal of rotation direction. The second, Venus was flipped. Its original spin never reversed in its own frame. The planet's axis was reoriented in space, tipped nearly upside down, so that a spin that was once prograde in the original orientation now appears retrograde from outside because the planet is almost inverted. Think of a spinning top. Say it is spinning counterclockwise when you look down at it from above. Now pick it up and flip it over. Without changing anything about the spin itself, It now appears to spin clockwise when you look down at it again. The top has not changed. Your vantage relative to the top has changed. From outside the top, the rotation looks reversed. From inside the top's own frame, nothing has altered at all. These two histories look identical from the outside. Same final tilt, same final rotation direction, same angular momentum vector pointing the same direction in space. No measurement of Venus's current state can tell you which one happened. But they are not the same physically, not even close. A true rotational reversal requires mechanisms that acted directly on the spin rate itself, forces that bled rotational energy away, and reversed the sense of spin across billions of years. Atmospheric tides are the most plausible candidate for this pathway. A true flip requires something that reoriented the spin axis in space, which almost certainly means a large body interaction, a massive impact, a gravitational coupling with another object, or something that torqued the planet's axis without necessarily slowing the spin rate dramatically. Different physics, different timescales, different requirements on what the early solar system looked like, different predictions for what else we might find in the atmosphere or the surface. Compared to Uranus, Uranus is tilted at about 98 degrees from vertical, rolling on its side as it orbits the Sun. The best hypothesis involves an early massive impact, possibly from an object roughly Earth-sized, that tipped the planet over. But Uranus is tilted, not inverted. And Uranus has something Venus does not. Its moons orbit in Uranus's equatorial plane, suggesting they formed or were captured into that configuration after the tipping event. The moons carry a historical record. They are witnesses to something that happened. Venus has no moons, no equivalent record, no witnesses. So we are left with two possible histories, two different sets of physics, two different stories about what the early solar system did to a planet that was supposed to be Earth's twin, and no way yet to distinguish them from the outside. The spin is altered, the record is erased, and the meaning of the word backward has two answers, both geometrically valid, both historically possible, and currently indistinguishable from each other. The question of which one is true would turn out to be harder to answer than anyone initially expected. Set the interpretation aside for a moment. Set aside the two possible histories, and the erased record, and the geometrically identical outcomes. Just feel how slowly Venus turns. Earth's equator is moving right now, not drifting slightly, moving at roughly 1,040 miles per hour, about 1,670 kilometers per hour, in the direction of rotation. You cannot feel it. Nothing in your daily experience hints at it, but the ground beneath you is traveling faster than a commercial aircraft, continuously, carrying you through space as the planet completes its daily turn. That speed is the inheritance of a rotating nebula, preserved across 4.5 billion years, expressed every second in the quiet hum of a world that has never slowed down. Venus's equator is also moving, at about 4 miles per hour, roughly 6.5 kilometers per hour. That is walking speed. A person moving at a brisk pace could match the motion of Venus's surface. A person in good shape could outrun it. Not outrun a vehicle, not outrun a current, outrun a planet. A planet nearly the size and mass of Earth, a body so similar in bulk that early planetary scientists described it as Earth's twin, is turning like a lathe set to its lowest possible setting, almost still. The surface barely moves. That comparison is worth sitting with, not for a moment, for long enough to feel how strange it is. When we say Venus rotates slowly, the word slowly does not quite carry the weight of the reality. 4 miles per hour is not slow in the way that a glacier is slow, or that continental drift is slow, where the motion exists but escapes ordinary perception. 4 miles per hour is a pace a human body knows. It is the speed of a walk to the corner. It is the speed of a child running alongside a car in a parking lot. Applied to a planetary surface, it stops making intuitive sense, and yet the number is correct. Venus's equatorial surface moves at walking speed. The sidereal period, which is the rotation of Venus measured against the distant stars, takes 243 Earth days to complete one full turn. But here is a detail that makes the geometry even stranger. The solar day on Venus, the time from one sunrise to the next, is not 243 days. It is shorter, roughly 116.75 Earth days, just under 117. The reason comes from geometry. Venus rotates in the retrograde direction while orbiting the Sun in the prograde direction, the same direction as every other planet. Those two motions work against each other. As Venus moves along its orbit, the Sun appears to shift position in Venus's sky. The planet's backward spin and its forward orbital motion combine in a way that shortens the apparent solar day relative to the pure rotation period. The result is that a Venusian year, which lasts about 224 Earth days, contains just under 2 full sunrise to sunset cycles. The Sun rises twice per Venusian year. Roughly every 117 Earth days, once, the Sun climbs across the sky from west to east, and sets. Wait, the solar day is shorter than the sidereal day. On a planet with a retrograde rotation, the calendar arithmetic runs backward from what intuition expects. Most planets have a solar day slightly longer than their sidereal day, because their prograde spin and prograde orbit work in the same direction. Venus's rotation works against its orbit, compressing the apparent solar day below the raw rotation period. 2 sunrises per year. That is the texture of time on Venus. Now consider what this slowness does to the physics. On Earth, the rapid rotation produces the Coriolis force, the deflection of moving air masses caused by the spinning reference frame beneath them. That deflection organizes the atmosphere into the banded circulation patterns we recognize. Trade winds, jet streams, the spiraling arms of hurricanes. The Coriolis force does not move air on its own. It redirects air that is already moving, giving the circulation structure. Fast rotation means a strong Coriolis effect. Strong Coriolis means organized banded atmospheric patterns. Venus rotates slowly. The Coriolis force on Venus is weak, not weakened slightly, drastically reduced. The result is that Venus's atmospheric circulation follows a very different geometry than Earth's. Instead of the banded, latitude-organized patterns that fast rotation produces, Venus's atmosphere develops a circulation dominated by direct transfer from the hot side to the cool side, a more direct convective flow that the weak Coriolis force cannot organize into tight bands. But the day-night temperature contrast, which you might expect to be extreme given that one side faces the Sun for nearly 60 Earth days at a stretch, turns out to be surprisingly small. The thick atmosphere moves heat around the planet efficiently enough that the temperature difference between the day side and the night side is modest. The slowness of the rotation does not produce the scorching day and frozen night that the slow cycle might imply. The atmosphere is doing the work that the planet's rotation rate left undone. All of this is consequence of the 4 mile per hour surface. But here is the deeper implication, the one that matters most for understanding how Venus's spin might continue to change. When a planet rotates quickly, small forces don't accumulate. The planet cycles through alignments so fast that small torques, the tiny twisting forces exerted on it by the Sun's gravity acting on its atmosphere, by tidal distortions, by long-period resonances, tend to average out. The planet moves through the influence before the influence can build. Fast rotation is a kind of immunity to small persistent pushes. Slow rotation removes that immunity. When a planet rotates slowly, small torques have time to act. The same force that would average to nearly 0 over a fast rotator's quick cycle has days or weeks or decades to push in the same direction before the geometry changes. Small becomes dominant. Influences that would be negligible on Earth become meaningful at Venus. The planet grows sensitive to physics that fast-spinning worlds can ignore. This is the condition Venus is in right now, rotating slowly enough that small persistent torques can reshape its spin over geological time. And the slow rotation itself may be both the outcome of something that happened long ago and the precondition for further change. A feedback loop. The planet slows for some reason, and in slowing, it becomes more susceptible to the forces that slow it further. How that feedback works, what forces are actually involved, what the atmosphere has to do with it at a physical level rather than a climatic one, is where the next part of this story goes. And the most powerful of those influences has been overhead the whole time. Venus's atmosphere is not a backdrop. It is not a passive layer of gas sitting between the surface and space. It is an active participant in the physics of how this planet spins. Understanding that changes everything about how we read Venus's rotation. But to understand why, we have to start with the scale. The atmosphere of Venus is roughly 93 times more massive than Earth's. Not denser in some relative sense, not heavier by a modest margin, 93 times. If you could somehow pile all of Earth's atmosphere into a single column above your head, and then pile 92 more identical columns on top of that, you would approach what Venus's surface endures continuously. The surface pressure is about 92 times what we experience at sea level. Oceanographers use a comparison that makes this feel real, that pressure is roughly equivalent to diving 900 meters beneath Earth's ocean. Not 30 meters, the depth of a recreational dive. Not 100 meters, where the crushing weight becomes genuinely dangerous. 900 meters, the kind of depth that collapses submarines. The surface temperature holds at around 465 degrees Celsius, hot enough to melt lead, hot enough that any probe sent to land on Venus has survived only about an hour before the heat and pressure destroyed it. The composition is about 96.5% carbon dioxide, with the remainder mostly nitrogen and traces of sulfur dioxide, water vapor, carbon monoxide, and argon. The clouds are not water. They are droplets of sulfuric acid, dense enough to hide the surface completely, reflective enough to make Venus the brightest object in the night sky after the moon. And the greenhouse effect produced by all that carbon dioxide and cloud cover makes Venus the hottest planet in the solar system. Not Mercury, Venus. Despite Mercury sitting far closer to the Sun, Venus runs hotter because its atmosphere traps energy with extraordinary efficiency. A runaway greenhouse taken to its logical conclusion. Something else was happening. All of that describes the surface and the lower atmosphere. The crushing scale, the scorching heat, the acid clouds. What matters most for Venus's rotation is something happening high above all of it. At around 65 kilometers altitude, where the thick cloud layer sits, the atmosphere is moving at a completely different speed than the planet beneath it. Not somewhat faster, not measurably quicker in a way that requires instruments to detect. The upper cloud layer races around Venus in approximately 4 Earth days. The surface beneath it takes 243 Earth days to turn once. The atmosphere is moving roughly 60 times faster than the planet it sits on top of. This is what planetary scientists call superrotation. The word sounds almost calm, but the phenomenon is striking. Imagine a record spinning on a turntable, except the record is moving 60 times faster than the turntable beneath it. Not slipping a little, not wobbling at the edges. Spinning independently at a completely different rate, in a stable and persistent pattern that has continued for as long as we have been able to observe it. At cloud level, wind speeds reach around 100 meters per second. That is about 360 kilometers per hour. A Category 5 hurricane, sustained, wrapping continuously around the entire planet. We first identified superrotation in the 1960s by tracking features in ultraviolet images of Venus's cloud deck. The clouds have patterns, subtle brightness variations at UV wavelengths that are invisible to the naked eye. And by watching those patterns move, scientists confirmed that the upper atmosphere was circling the planet far faster than the surface below. Later missions refined the picture. Japan's Akatsuki spacecraft arrived at Venus in 2015 and has been observing the cloud dynamics in detail ever since, mapping wind speeds, tracking how superrotation varies with altitude and latitude, slowly building a more complete picture of a phenomenon that still lacks a fully accepted explanation. But for the question of Venus's spin, the exact mechanism producing superrotation matters less than the consequence. The atmosphere and the solid planet are nearly decoupled from each other rotationally. They are doing different things, and that matters because the atmosphere carries something important. It carries angular momentum, the same quantity that governs how planets spin. A 93 times more massive atmosphere moving at 60 times the surface speed holds a significant reservoir of rotational energy, and that reservoir does not sit in isolation. It exchanges momentum with the solid planet beneath it. The exchange happens through 2 pathways. The first is surface friction. Where the base of the atmosphere meets the surface of the planet, viscous drag transfers momentum between them. The second is more subtle, thermal tides. As the sun heats one side of Venus, the atmosphere on that side becomes less dense, creating a bulge of lower density air that shifts position as the planet slowly turns. That bulge is gravitationally and mechanically coupled to the planet, and as the planet rotates under it, the bulge exerts a torque on the solid surface. Not a metaphorical torque, a real force acting on the rotation of the planet. The consequence reshapes the entire problem. Venus's rotation cannot be modeled as a rigid body spinning in isolation. That approach is incomplete from the start. The planet must be treated as a coupled system. Solid planet plus atmosphere, exchanging angular momentum continuously, with the atmospheric component capable of driving long-term changes in planetary spin. Over geological time, atmospheric torques can push Venus's rotation in directions the planet would never reach on its own. The atmosphere is not a passenger, it is a driver. This is the crack in the rigid body picture that earlier theories of Venus's spin missed or underweighted. Treat Venus as a simple ball, and the physics closes off too early. Open the picture to include the atmosphere as a dynamically active layer, and the space of possible spin histories expands considerably. And then the record deepens further. The coupling strength between the atmosphere and the solid planet depends on the atmosphere's density, composition, and temperature. Those are not fixed properties. They change over geological time. Early Venus may have looked radically different from the Venus we observe now. Some models suggest it may once have had liquid water, possibly even oceans, before conditions shifted. If Venus's atmosphere was once thinner or denser or structured differently, then the torques it exerted on the planet were different. The feedback between spin and atmosphere runs both ways. The atmosphere shapes the rotation, and the rotation shapes the atmospheric circulation that produces superrotation in the first place. What this means is that Venus's spin history is entangled with its atmospheric history, and we do not fully understand Venus's atmospheric history. We do not know what it looked like 3 billion years ago, or 2 billion years ago, or even 1 billion years ago. The deeper we look, the more the current record turns out to depend on other records we have also lost. The atmosphere overhead is not a clue, it is a co-conspirator, and how it and the solid planet have pushed each other across billions of years is exactly the territory the next part of this story enters. But before the quiet explanations get their hearing, the loud one deserves its moment. When Venus's rotation was confirmed in the mid-1960s, the first reflex was not surprise at the complexity of the problem. The first reflex was simple. Something hit it. Something large, moving fast, struck Venus hard enough to send it spinning the wrong way. And that instinct made complete sense. The solar system is not a gentle place. Walk through the evidence. The moon's cratered face, scarred by billions of years of bombardment, tells a story of relentless impact. Mercury carries a battered surface that preserves some of the oldest collision records in the inner solar system. Mars holds vast basins carved by enormous ancient strikes, and Earth itself formed its moon through an impact so violent that it partially vaporized both worlds, with the resulting debris cloud coalescing into the satellite we see today. The early solar system was a demolition yard. Large bodies colliding with other large bodies was not the exception. It was routine for the first few 100 million years. So when scientists in 1965 looked at Venus and asked what could reverse a planet's spin, the first papers that circulated floated the impact answer in general terms. Something enormous hit Venus. That was the working idea. Here is what that something would have to look like. To reverse Venus's spin, you cannot tap it lightly. You need to deliver angular momentum in the opposite direction, enough to bleed the original prograde spin to zero, and push it past zero into retrograde, while leaving the planet structurally whole. Run the numbers. Calculate Venus's current angular momentum. Compare it to what an Earth-like original spin would have provided. Solve for the impactor that bridges that gap. The answer that comes back is a body roughly Mars-sized, or larger, a few thousand kilometers across, hitting Venus not head-on but obliquely, at significant orbital velocity, the way a cue ball clips a billiard ball at an angle to redirect it. The geometry has to be right. Strike it straight, and you get a catastrophic merger, not a spin reversal. Strike it at the correct angle with the correct mass, and you can, in theory, flip the spin while leaving Venus recognizably intact. That size is not arbitrary. A Mars-sized impactor puts this event in roughly the same ballpark as the moon-forming impact, one of the most consequential single events in Earth's history. So the drama of Venus's rotation seemed to be matched by the drama of the explanation. The planet behaves dramatically. The cause is dramatic. The story felt complete. The picture did not hold. When you actually follow the physics past the geometry and into the energy budget, the explanation starts to come apart. An impactor Mars-sized or larger, striking at significant orbital velocity, releases energy on the order of 10 to the 32nd joules. That number is nearly impossible to picture. So think of it this way. It is enough energy to melt a substantial fraction of Venus's entire mantle. Not the surface, the mantle, the deep rocky layer that makes up most of the planet's volume. It is enough to eject enormous amounts of crustal material into space. Enough to vaporize any oceans Venus may have held at the time. Enough to strip most of the atmosphere away entirely. And there is a consequence that follows directly from all that ejected material. When an impact blows debris into orbit around a planet, that debris does not just disappear. It collects. It gathers into rings. And rings, given enough time, reaccrete into moons. This is precisely what happened at Earth. The moon-forming impact left behind the moon. The mechanism is well understood. Venus has no moons, 0. Earth has 1. Mars has 2 small ones, almost certainly captured but present. Even Mercury, which has no moons, preserves a detailed crater record on its ancient surface. Evidence of impacts written in the rock. Venus has neither. No moons and no globally visible impact structure of the scale that an event this violent should have produced. The planet that was supposedly struck by a Mars-sized body shows none of the expected aftermath. Now, one possible response to this is to note that Venus's surface was completely resurfaced within the last roughly 500 million years. We covered that earlier. If a global volcanic event buried and erased everything before it, then the absence of a visible impact structure might not mean no impact occurred. The scar might simply have been paved over. That argument is technically available, but notice what it costs. It requires that the impact occurred, that the impact was violent enough to reverse the planet's spin, and that subsequent geological activity then erased the impact structure, the atmospheric signature, and every other surface-level trace, while leaving no moons behind either. You are stacking one implausibility on another. The evidence is gone because something destroyed it, not because nothing happened. That is a hypothesis that cannot be falsified. It explains everything by requiring everything to have been erased. The timing problem cuts in from a different angle. If the impact happened early, while Venus was still accreting and still partially molten, then the planet could potentially re-equilibrate, the way Earth re-equilibrated after its own giant impact. But here's the catch. Continued accretion after an early impact would tend to add prograde angular momentum, gradually restoring the spin toward the expected direction. An early impact might be undone by everything that followed it. If the impact happened late, after accretion was complete, the debris and surface evidence problems return in full force. A solid, fully formed planet struck hard enough to reverse its spin should carry the marks of that event, and Venus does not. Through the 1970s and into the 1980s, increasingly sophisticated planet formation simulations made this harder and harder to ignore. The community did not abandon the impact hypothesis outright. Nothing better had replaced it yet, but enthusiasm quietly faded. The papers became more cautious. The language shifted from confident assertion to considered possibility, and researchers began to look elsewhere, toward mechanisms that did not require a single catastrophic event, and all the evidence that should have followed from it. The most dramatic answer turned out to be the weakest. The obvious explanation, the one that felt satisfying the moment you reached for it, could not survive contact with its own consequences. A blow large enough to flip Venus should have left the solar system's most documented calling card, a moon, and it left nothing at all. That gap between what the hypothesis predicts and what Venus shows is not a small discrepancy. It is the center of the problem, and the slower, quieter mechanisms that scientists began reaching for next would prove to be far stranger than a single violent collision ever could. If a single later blow could not do it, perhaps Venus was never struck at all. Perhaps it was born this way. Around 2008, a different version of the catastrophic explanation began appearing in the literature. Not a giant impactor striking a fully formed Venus and reversing a spin that was already set. Something earlier. Something more fundamental than that. Two protoplanets, each roughly the size of Mars, colliding during the accretion phase itself before Venus had finished forming. The merger would not have changed Venus's rotation. It would have created it. The distinction matters enormously. The late impact version required reversing a spin that already existed, which meant bleeding away enormous angular momentum and leaving debris behind. The merger version requires no reversal at all. The geometry of the collision sets the rotation at the moment of formation. Venus does not need to be turned around. It is assembled spinning the wrong way from the start. This fits naturally into what we know about the early solar system. The accretion phase was not a smooth, orderly process. It was chaotic. Mars-sized bodies were common. The terrestrial planets grew through repeated collisions, not through a gradual accumulation of pebbles. Earth's moon-forming impact is the most famous example of that violence, but it is not unique. It is simply the one that left the clearest surviving evidence. Others happened. Many of them left almost nothing behind. N-body simulations, which track the gravitational interactions of many bodies over time, show that a small but non-zero fraction of formation pathways produce retrograde rotators through merger geometry alone. A few percent. Not the dominant outcome, but a few percent is enough. We are not trying to explain 8 planets spinning backward. We are trying to explain one. A low probability event is entirely acceptable when you only need it to happen once. The merger hypothesis also handles the moon problem better than any version of the late impact story ever could. When a large body strikes an already formed planet, it ejects material into orbit. That material tends to collect into a ring and then reaccrete into a moon. That is precisely what happened when a Mars-sized body struck early Earth. The moon is the product of that geometry. But timing matters. Earth's moon formed from an impact that occurred relatively late in the accretion phase, when the planet was largely assembled and its gravity well was deep and stable. Debris ejected at that stage could settle into a lasting orbit. An earlier merger, one happening while the planet itself was still growing, produces a different outcome. The debris tends to fall back into the still accreting mass. It gets swallowed. The planet is too diffuse, too dynamic, for a stable moon to take hold. Venus's merger, if it happened, could easily have occurred early enough and with the right geometry to leave no lasting satellite. Not because the event was smaller, because the timing was different. That is the honest strength of this version of the story. It requires no exotic physics. It invokes mechanisms that we know operated during planetary formation. It avoids the moon problem, and it leaves room for everything that came afterward. The atmospheric evolution, the water loss, the slow reshaping of the spin over billions of years. But the reality was different. Accepting the merger hypothesis requires accepting a chain of specific conditions, each of which had to be true simultaneously. 2 Mars-sized protoplanets had to exist in the right region of the inner solar system at the right moment. They had to approach each other with the right geometry. They had to stick together rather than bouncing apart or fragmenting into smaller bodies. And the resulting planet had to settle into an orbit close enough to its current one that the subsequent history of the solar system did not dislodge it. Chain those requirements together, and the joint probability drops. Not to 0, but low enough to remain uncomfortable. And there is a harder problem still. The merger happened, if it happened at all, 4.5 billion years ago. It left no surface record. The geological history of Venus was erased long before any instrument could have observed it. The event is not just unconfirmed, it is unconfirmable by any direct means we currently possess. That is the reality of working on Venus's deep past. The catastrophic event family, whether late impact or early merger, is not obviously wrong. It is consistent with formation physics. It is consistent with what the early solar system looked like. It is a respectable contender. But the evidence needed to prove it is buried under 4.5 billion years of planetary history. And a significant fraction of that history was itself erased in a single global event 500 million years ago. Which brings the question to where it always eventually arrives on Venus. What evidence survives? The geological record does not, but the atmosphere does. And the atmosphere has been keeping a secret. Hidden inside Venus's atmosphere is one of the only surviving fragments of information about what Venus was like in its earliest history. It comes from hydrogen, specifically from two versions of hydrogen that are chemically almost identical but physically distinct in one important way. Regular hydrogen, the most common element in the universe, has a single proton in its nucleus and nothing else. Deuterium, sometimes called heavy hydrogen, has one proton and one neutron, roughly twice the mass of its ordinary counterpart. Both atoms behave nearly identically in chemical reactions. Both bond with oxygen to form water, but their masses are different, and that difference matters when a planet is trying to hold on to its atmosphere. When solar radiation strips hydrogen from a planet's upper atmosphere, the lighter atoms escape more easily. A regular hydrogen atom needs less energy to reach escape velocity than a deuterium atom does. So when hydrogen bleeds away into space over billions of years, regular hydrogen goes first. Deuterium is left behind. The longer this process continues, the higher the ratio of deuterium to regular hydrogen becomes in the remaining atmosphere. The ratio is a clock, a chemical fossil, a record of how much hydrogen has been lost. Earth's deuterium to hydrogen ratio sits at roughly 1.5 times 10 to the power of -4. That number reflects the inner solar system average, consistent with water delivered to Earth during formation and mostly retained ever since. Venus's ratio is about 150 times higher than Earth's. Not slightly elevated, not enriched by a modest margin, 150 times. That number represents an enormous quantity of lost hydrogen, and the most natural source of atmospheric hydrogen on a rocky planet is water. Water molecules broken apart in the upper atmosphere by solar radiation, with the hydrogen escaping into space and the oxygen remaining behind or combining with surface rock. Working backward from the enrichment, estimates suggest Venus may once have held enough water to cover its entire surface to a depth of several hundred meters, comparable in total volume to Earth's oceans. Not a thin film, not a trace residue, enough to constitute a real ocean world, at least in terms of total water budget. That possibility carries weight. It raises the question that lies just beneath the surface of every part of Venus's history. Was Venus once habitable? Not in some marginal or technical sense, but genuinely habitable, with liquid water on its surface and temperatures that could have sustained chemistry complex enough to matter? And if so, for how long? And what changed? The answer to what changed almost certainly involves the runaway greenhouse effect. As the sun gradually brightened over its early history, rising temperatures began evaporating water from Venus's surface. Water vapor is itself a greenhouse gas. More vapor meant more warming, which meant more evaporation, which meant still more vapor. The process accelerated until the oceans were gone entirely. The water vapor broken apart in the upper atmosphere. The hydrogen scattered into space, and the oxygen absorbed into the surface rock or lost as well. But the timing of that process, and whether it operated alone or was accelerated by something catastrophic at the beginning, depends on Venus's rotation. Climate dynamics depend on how heat is distributed across the planet. Heat distribution depends on atmospheric circulation. Atmospheric circulation depends on how fast the planet is spinning. And how fast Venus was spinning in its earliest period depends on exactly the question the merger and late impact hypotheses are trying to answer. The two stories make different predictions. A catastrophic early merger that set Venus spinning backward from the start would have produced different early climate dynamics than a Venus that began prograde and was gradually slowed and tilted by atmospheric tides over billions of years. Different dynamics, different rates of water loss, different isotope signatures in what remains. The deuterium to hydrogen ratio is not just a relic of water loss. It is a potential discriminator between the two families of explanation for how Venus became the planet it is today. NASA's Da Vinci mission will measure those ratios with a precision that no previous instrument has achieved. It will descend through Venus's atmosphere in stages, sampling gases at multiple altitudes, building a chemical profile of what the atmosphere actually contains. The isotope data Da Vinci returns will constrain the water loss history with far more precision than current measurements allow. That story is worth returning to when the missions themselves are the subject. For now, the point is this. Venus's geological record is gone, but the air above it still carries a number, 150 times Earth's deuterium to hydrogen ratio, that encodes a history of staggering water loss, and possibly an entire vanished ocean. The catastrophic explanation for Venus's spin remains a contender. The chemical evidence suggests that whatever happened to Venus happened on a scale large enough to remake the planet entirely, and the question of whether that remaking began at the very first moment of Venus's existence or accumulated slowly across billions of years is exactly what the next part of this story works toward answering. And if nothing ever struck Venus at all, if no body crashed into it and no merger set its spin at birth, then something else must account for everything we see. Something quieter, something that has been working the entire time. In the early 2000s, two planetary dynamicists named Alexandre Correa and Jacques Lascar published a series of papers that proposed exactly that. Their argument was not that the catastrophic explanations were impossible, it was that they were unnecessary. Venus's current rotation, they proposed, could be the natural outcome of billions of years of slow evolution, driven by forces that never stopped acting. No single violent moment required, just time and physics and three invisible torques pulling at Venus in different directions across the full span of its history. The conceptual shift was important. We tend to think of a planet's rotation as something set at birth, an initial condition inherited from the cloud it formed from, altered only by collision or capture. Correa and Lascar were proposing something different. A planet's rotational state, they argued, is not only what it started with, it is the sum of everything that has acted on it since. And if those forces act continuously, the rotation evolves. It drifts. It settles. It can reach entirely different endpoints depending on the balance between the forces and the conditions the planet happened to have. The initial spin matters less than you might expect. What matters is where the forces carry you. There are three of those forces acting on Venus. The first is the solar gravitational tide. The sun's gravity does not pull on Venus uniformly. It pulls harder on the near side than the far side. That uneven pull deforms Venus very slightly, stretching it into a shape closer to an ellipsoid than a perfect sphere. Like Earth's ocean tides, except that Venus has no oceans. So the solid rock of the planet itself is the thing that deforms. As Venus rotates, it drags those slight deformed bulges slightly out of alignment with the Sun-Venus line, and that misalignment produces a torque. That torque always opposes rotation. It is always working to slow Venus down, pulling it toward a synchronous lock with the Sun, the same kind of lock that keeps our moon always showing us the same face. Left alone, the gravitational tide would eventually bring Venus to a complete rotational stop relative to the Sun. One face pointed toward the Sun permanently, the other facing away forever. That is where gravity wants to take it. Then the data shifted. The second torque acts in the opposite direction entirely. The Sun heats Venus's day side. That heat expands the atmosphere, creating a region of lower density on the day side and a corresponding asymmetry in the atmospheric mass distribution. As Venus rotates, it drags that asymmetric atmospheric bulge with it, and the gravitational interaction between the displaced atmospheric mass and the solid planet below exerts a torque on the surface. This is the atmospheric thermal tide, and crucially, it pushes not toward synchronous lock, but away from it, toward retrograde rotation. The two main tides are in direct opposition. The gravitational tide says, slow down, stop, lock to the Sun. The thermal tide says no, spin backward. The third force is smaller, but not negligible. Venus has a liquid metal core surrounded by a solid, rocky mantle. Because the core and mantle are physically distinct layers with different densities and compositions, they can rotate at slightly different rates. Friction at the boundary between them transfers angular momentum back and forth. It does not drive the rotation in either direction the way the tides do, but it damps the evolution, smoothing out the transitions, coupling the core and the mantle as the planet changes, 3 torques, all continuously active, all depending on the same conditions: the rotation rate, the mass and temperature and composition of the atmosphere, the distance from the sun, the interior structure of the planet. And here is what Correa and Lasker found when they ran the simulations. They started Venus at a wide range of initial rotational states: fast prograde spins, slow ones, fast retrograde, near zero, everything in between, and evolved each one forward over billions of years, with all 3 torques operating. The planet did not simply decay to synchronous lock in every case. It did not simply spin up to fast retrograde in every case. Instead, it settled. Different starting points led to different final configurations. Some were prograde, some were retrograde, some were near zero. The system had multiple stable endpoints, multiple places where the competing forces found a balance and the rotation stopped changing. Think of it like a landscape with several low points. A marble rolled across that landscape will come to rest in one of the valleys, not necessarily the deepest one, but whichever one it happened to roll toward. The marble does not care where it started. Given time, it finds a valley, and it stays there. Those valleys are what physicists call attractors, stable rotational states that the physics naturally guides the planet toward, regardless of where it began. The current Venus, slow retrograde rotation, a period of 243 days, an axial tilt close to 180 degrees, is consistent with one or more of those attractors. Not a fluke, not the scar of a catastrophe, simply where the physics carried it. One of several places the marble could have landed, given Venus's particular atmosphere and interior and distance from the sun. The reveal is not a dramatic one. That is almost the point. Nothing extraordinary happened. No body arrived at the wrong moment from the wrong angle. No merger set the spin backward at birth. 3 quiet forces worked across billions of years, fighting each other, balancing, shifting the planet's rotation a tiny amount with every orbit, every season, every year, never stopping. And when enough time had passed, Venus was where it is now. But the reveal has a second layer, and this is the one that matters most. Without the atmosphere, none of it works. The thermal tide, the torque that opposes synchronous lock and drives rotation toward retrograde, exists because Venus has a massive, thermally active, super-rotating atmosphere. We established earlier that this atmosphere is nearly 100 times more massive than Earth's, that it circulates at wind speeds comparable to a sustained Category 5 hurricane at cloud level, that it super-rotates at 60 times the speed of the solid surface beneath it. All of that mass and energy means the thermal tide is strong enough to compete with the gravitational tide, strong enough to push the rotation into retrograde instead of into lock. Without that atmosphere, the thermal tide torque would be negligible. The gravitational tide would win easily, pulling Venus into synchronous lock with the sun. Venus would become a tidally locked world, one face always toward the sun, the other always dark, and the slow retrograde rotation we observe would not exist. The atmosphere is not incidental to the story of Venus's spin. The atmosphere is the engine, which means Venus's rotation is not a property of the solid planet alone. It is a property of the system. The solid planet and the atmosphere together, coupled and co-evolving across billions of years, each shaping the other, neither one fully separable from the other's history. The rotation we observe is the product of that coupling. The tilt we observe, the slowness, the retrograde direction, all of it emerges from the interaction between the planet and the thick, restless atmosphere that has enveloped it since nearly the beginning. Venus is not a mystery hidden in the rock. It is a mystery written in the air above the rock. This is a statistical explanation, not a deterministic one. Correa and Lasker are not claiming that Venus was always destined to arrive here, that only these initial conditions could have produced this outcome. They are saying that this outcome is one of several the physics allows, and that given what Venus actually has, a massive atmosphere, a liquid core, this particular distance from the sun, this outcome is fully consistent with reaching the current configuration without any catastrophe at all. We do not need a smoking gun. We may simply need patience and the right starting conditions. But the 3 torques framework depends on knowing those starting conditions with some precision, and we do not know them. We do not know exactly what Venus's early atmosphere looked like, how massive it was in the first billion years, how its composition evolved. We do not know the precise interior structure of Venus, the exact size and viscosity of the liquid core, the coupling strength at the core mantle boundary. The torque parameters are imperfectly constrained, and different assumptions about them shift the attractor landscape, changing which final states the planet could reach and from how wide a range of initial conditions. So, the framework is powerful, it may be correct, but it rests on atmospheric and interior parameters that remain partially unknown. And determining those parameters precisely would require exactly the kind of deep atmospheric measurements that the next generation of missions is being designed to provide. The 3 quiet talks may have done everything. The question is whether we can prove it. Even this quiet explanation, examined closely, splits in 2. The Correa-Lasca framework is elegant. It needs no catastrophe, no smoking crater, no vanished moon. It asks only that we accept time and physics and the slow work of 3 continuous talks. And for a moment, when you first encounter it, it feels like the answer. Not one answer among many, the answer. But here's where it gets strange. Even within that single framework, 2 entirely different histories can produce the same Venus sitting in front of us today. 2 pathways, 2 stories, 1 ending. And from where we stand, looking up at that bright, featureless point of light, we cannot tell which one actually happened. The first pathway is gradual reversal. Venus begins its life spinning in the prograde direction, the same direction every planet inherits from the original disk. The 3 talks begin their work. Over billions of years, the combined gravitational and thermal tides slowly drain the rotation. The spin rate drops. It drops further. It passes through 0. Then it crosses over into retrograde territory, and the thermal tide, which had been pushing against synchronous lock the whole time, finds a new equilibrium. It settles. It holds. The rotation stabilizes at a period of 243 days. Retrograde. Throughout all of this, the axial tilt stays small. The planet remains right side up. Only the direction of spin changes. What you get at the end is a planet spinning slowly backward, axis nearly upright, looking exactly like Venus looks today. The second pathway is an axial flip. Venus also begins prograde, but instead of the rotation rate draining smoothly toward reversal, the torques destabilize the rotation axis itself. The axis begins to migrate. It tilts. It tilts further. It passes through 90 degrees, the point at which the planet is spinning on its side, and continues past. It approaches nearly 180 degrees. The planet is now effectively upside down. In Venus's own reference frame, the direction of spin may not have changed dramatically at all. The same rotation that was prograde before is still spinning roughly the same way from the planet's internal perspective. But from outside, from every other planet in the solar system, from a telescope on Earth, it appears retrograde, because the planet tipped over. What you get at the end is also a planet spinning slowly backward, axis nearly inverted, looking exactly like Venus looks today. Both pathways end at the same address. The internal structure would be indistinguishable. The atmospheric composition would be indistinguishable. The mass distribution, the gravity field, the rotation period of 243 days, all of it matches in both cases. You could observe Venus for a century with every instrument currently available, and you would not be able to tell which path brought it here. This is what scientists call observational degeneracy. Multiple histories collapsing into the same present. The planet looks identical regardless of which story is true, and we do not have the evidence to break the tie. A preserved early magnetic field would help. If Venus had one, it would have recorded the orientation of the rotation axis at different points in history, layer by layer, like a geological compass reading frozen in ancient rock. Venus has no detectable global magnetic field now, and no remnant magnetic signature in the crust that could carry that early record. The compass was never set, or it was erased. Ancient crust would help. If enough of the original surface had survived, it might carry the characteristic deformation patterns of one evolutionary pathway versus the other. Features that form differently depending on whether the planet flipped its axis or reversed its spin. But the crust is gone. The resurfacing event that occurred hundreds of millions of years ago wiped that record clean. Moons would help. A moon formed during or shortly after the key transition would have its orbital plane locked to the rotational state Venus was in at that moment. Its orbit would carry the memory, but Venus has no moons. Simulations suggest that the relative probability of the two pathways depends entirely on which assumptions you plug into the torque equations. Under some choices of atmospheric mass and interior viscosity, the axial flip dominates overwhelmingly. Under other choices, gradual reversal is more likely. The answer changes with the parameters, and the parameters remain imprecisely known. So now count the viable histories. There are at least 4. The first is gradual slow reversal within the slow physics framework. The second is gradual axial flip, also within the slow physics framework. The third is early merger with retrograde geometry. Venus's rotation set at the moment of formation itself, when 2 protoplanets collided at the right angle and the right timing to produce a retrograde planet before the question of spin change ever arose. The fourth is a late catastrophic impact, a massive body striking a fully formed Venus obliquely, bleeding its angular momentum and reversing the spin in a geologically brief event. All 4 can produce the observed state. All 4 are consistent with Venus as it exists right now. Think about what that means. We are not choosing between a correct answer and a set of wrong ones. We are standing in front of 4 different explanations, each physically plausible, each consistent with everything we can currently measure, and we cannot eliminate any of them. Not one. The data does not reach far enough back to distinguish between them. The evidence that could discriminate is unavailable, not slightly incomplete, systematically unavailable. Billions of years of volcanic resurfacing have repaved the surface, erasing the geological record that might carry the fingerprints of formation or early evolution. The atmosphere has cycled and transformed across timescales we cannot fully reconstruct. Whatever was written in the early crust, whatever the spin axis recorded in the first billion years, whatever debris field or deformation pattern one pathway would have left, and another would not, it is gone. And here is the deepest part of the problem. It is not simply that we lack instruments. It is not simply that we have not looked carefully enough. It is that Venus has been, across its entire history, methodically destroying the evidence. Every eruption that resurfaces a few more kilometers of crust removes another page of the record. Every atmospheric cycle that converts one chemical into another overwrites another chapter. The planet has not been passive. It has been active, and its activity has been, from the perspective of anyone trying to understand its origin, an act of continuous erasure. We are not archaeologists who arrived too late to the dig. We are archaeologists who arrived to find the site still burning. The 4 viable histories converge on one present. And the question of which history is real is not simply waiting for better data. It is waiting for data that Venus may never allow us to have. That is not a failure of science. It is a fact about this particular planet. And understanding that fact, grasping exactly what has been erased and why it cannot be recovered, turns out to be its own kind of discovery. When the clear answers run out, the field does not stop. It wanders into the stranger territory. And that wandering, far from being undisciplined, is one of the signs that a science is healthy. The gaps in the standard story are real, they are acknowledged, and they invite ideas that would have seemed implausible a generation ago. One of those ideas involves a planet that no longer exists. Some simulations of the early solar system suggest that the inner planets we see today may not be the complete original set. There may have been a 5th terrestrial planet, one that scientists informally call Planet 5, not a gas giant lurking at the outer edge. A rocky body, perhaps Mars-sized, orbiting in an unstable region, somewhere between Mars and the asteroid belt or in another configuration, that the gravity of its neighbors could not sustain indefinitely. The simulations that produce it do so because they are trying to explain something that the current planetary arrangement struggles to account for: the late, heavy bombardment. Around 3.9 billion years ago, the inner solar system experienced a concentrated pulse of impacts. The moon's surface records it. So does Mercury's. Craters from that period are stamped across both worlds in densities that suggest something reorganized the asteroid belt and flung material inward in unusual quantities. One proposed trigger is orbital migration by the outer planets. Another is Planet 5 itself, drifting into an unstable resonance, perturbing asteroid orbits as it destabilized, and eventually being ejected from the solar system entirely, or swallowed by the sun, or disrupted by a collision it did not survive. Here is where Venus enters the story. If Planet 5 existed, it did not simply vanish cleanly. Before it was gone, it moved, it approached. A close gravitational encounter between a wandering Mars-sized body and an early Venus could have delivered an angular momentum transfer significant enough to tilt Venus's rotation axis, or alter its spin rate, or both. Not a collision, not a merger. A near miss, close enough and massive enough to leave a signature. The idea is dynamically coherent. The evidence, though, is indirect. It rests entirely on simulation outputs, and simulations of the early solar system are sensitive to their starting assumptions in ways that make them suggestive rather than conclusive. Planet 5 remains a hypothesis with motivation, but without a smoking crater. A second exotic idea operates closer to home, and in some ways, it is even stranger. Some models propose that early Earth and Venus did not have the cleanly separated orbits they maintain today. The orbital architecture of the young inner solar system was less settled. Close approaches between Earth and Venus, episodic and repeated, could have allowed gravitational interactions to exchange angular momentum between the two planets. Not a collision. An exchange, mediated by gravity across distance, slowly tilting one or both worlds. The appeal of this idea is that it connects two things. Scientists already find puzzling. Why Earth and Venus are so similar in mass, size, and overall composition, yet so different in rotation, atmosphere, and habitability. The similarities suggest a shared origin environment. The differences suggest divergence afterward. An early angular momentum exchange between them could be part of that divergent story, but the evidence is indirect. The orbital histories required are not well constrained by anything we can currently measure. This remains a minority view, held by a small number of researchers, taken seriously as a possibility but not championed as a leading explanation. The most exotic of these ideas takes the problem of Venus's origin and relocates it entirely. What if Venus did not form where it is? What if it formed somewhere else in the solar system and was gravitationally captured into its current orbit later? This is the capture hypothesis, and it is appealing for a single, clean reason. If Venus formed elsewhere, with whatever spin orientation its original environment produced, and was then captured into its present orbit with that spin intact, retrograde rotation requires no reversal at all. It was always retrograde. The problem explains itself. The answer was stranger than expected. Capture works for moons. Triton, Neptune's largest moon, is almost certainly a captured Kuiper belt object, and its retrograde orbit around Neptune is the evidence. Capture is a real mechanism, but there is a significant difference between capturing a moon and capturing a planet. A moon capture requires a delicate alignment of velocity, geometry, and energy dissipation, but the numbers are manageable. A planetary capture for a body of Venus's mass requires conditions so precisely balanced that most planetary scientists consider the probability negligibly small. Not low, not unlikely, negligibly small. And then there is the composition problem. Not a minor footnote, the central objection. Venus is made of silicates and iron. Its bulk composition matches what you would expect from a body that formed in the inner solar system, close to the sun, where temperatures were high enough that only refractory materials could condense out of the protoplanetary disk. A body that formed farther out in the cooler outer regions would be expected to carry a much higher proportion of volatiles, materials like water and methane that condense at lower temperatures. Venus has almost none of those. Its surface is dry, its atmosphere contains barely a trace of water. If Venus formed far from the sun and migrated inward, its composition would betray that origin. It does not. The composition points inward from the beginning, not outward and inward afterward. The capture hypothesis founders on chemistry. It persists in the literature because it has not been formally ruled out, but most planetary scientists treat it as implausible. A minority view kept alive more by the difficulty of fully excluding it than by positive evidence in its favor. What all of these ideas share is not a common mechanism. What they share is a common context. They exist because modern simulations of the early solar system have revealed something that the textbook story of tidy planetary formation understates considerably. The early solar system was not orderly. It was chaotic in the precise, technical sense of that word. A dynamical system sensitive to initial conditions, capable of producing dramatically different outcomes from nearly identical starting points. The frameworks that capture this chaos have names: the Nice model, the Grand Tack hypothesis. Both emerged from detailed N-body simulations run in the early 2000s and refined since. Both describe an outer solar system that underwent significant orbital migration in the first hundreds of millions of years. Jupiter moved inward, substantially, before gravitational interactions with Saturn pushed it back outward. That inward then outward journey scattered objects throughout the solar system, reshaping the asteroid belt, delivering impactors to the inner planets, and reorganizing orbital resonances across the entire system. If Jupiter's migration was that dramatic, the inner solar system experienced the consequences. The calm arrangement we see today, 4 rocky planets in stable, well-separated orbits, is not a first draft. It is a surviving configuration, the end state of a process that included ejections, mergers, near misses, and cascading perturbations that no clean textbook model fully captures. Venus's rotation, read in that light, is not an anomaly waiting for one clean explanation. It is a noisy record of everything that happened to this planet across hundreds of millions of years of that chaos. Every encounter, every torque, every gravitational tug from a migrating Jupiter or a nearby protoplanet or a wandering Planet 5 left some contribution. The contributions accumulated. The final rotation is their sum, and none of the exotic hypotheses, not Planet 5, not the Earth-Venus exchange, not capture from elsewhere, produces a clean sum. Each carries its own flaw. Each leaves something unexplained or requires conditions that are difficult to justify independently. The field has turned them over carefully, examined them, and set them down without discarding them entirely. That is what a mature, honest scientific field does with ideas that are motivated but not confirmed. The chaotic early solar system is not itself a hypothesis that needs exotic rescuing. It is, at this point, the baseline. The question is not whether the early solar system was violent and disordered. The question is what specific sequence of that violence produced the Venus we measure today. And that question does not yet have a single answer. It has 4 viable histories, a collection of exotic alternatives without enough evidence to elevate or eliminate them, and a planet that has spent billions of years making sure the distinction between those histories is as hard as possible to recover. The exotic ideas are worth knowing, not because any one of them is likely to be right, but because together they illuminate how genuinely strange the early solar system was, and how that strangeness left its mark in places we are only beginning to look. And there are stranger and quieter possibilities still, before the trail leads back to the air itself. Some of them live not in the record of ancient impacts or early mergers, but in the mathematics of how spinning systems behave over time. Dynamical systems that involve multiple gravitational forces can develop resonances. A resonance is a configuration where 2 or more frequencies, orbital or rotational, fall into a simple relationship with each other. 1 rotation for every 2 orbits, 2 rotations for every 3. The system locks into that relationship the way a pendulum finds its natural rhythm, and once locked, it tends to stay there. The important thing about resonances is that a system does not have to start in one. It can drift into one. Gravitational interactions shift the frequencies slowly, and if the ratio happens to pass through a simple integer relationship, at the right moment, the system can be captured, trapped, stuck in that configuration even as the forces that pushed it there continue to evolve. Venus may have passed through a series of these resonant states across billions of years. The combined torques on Venus, gravitational tide from the sun, thermal tide from the atmosphere, friction at the core mantle boundary, create a system with multiple possible resonant endpoints, prograde configurations, retrograde configurations, various tilts. The transition between them may not have been smooth or gradual in the way the basic slow physics picture implies. It may have been chaotic, rapid, unpredictable rotational changes as the system moved between unstable resonant states before finally settling into the configuration we measure today. Not a slow drift to a stable valley. A system bouncing between valleys before finding one it could hold. That matters because it adds another layer of irretrievability. If Venus's spin history included rapid jumps between resonant states, the path from formation to present cannot be read backward from the present. Too many valid paths lead to the same endpoint. That is when the pattern broke. Even that picture assumes Venus started with a rotation that needed to be captured into its current state by forces operating after formation. There is an older and simpler idea, quietly persistent in the literature, that says Venus may never have rotated prograde at all. The protoplanetary disk from which Venus formed was not perfectly smooth. Local turbulence could, in principle, produce a region that rotated in the opposite direction from the overall disk, a counter-rotating eddy. A planet forming inside the eddy would inherit a retrograde rotation not as a scar from a later event, but as its birth condition. No reversal required, no catastrophic impact, no billions of years of slow torque accumulation, just a planet born spinning the wrong way. The appeal of this idea is real. It is one of the very few scenarios that requires no post-formation reshaping. Every other hypothesis has to explain how prograde became retrograde. This one does not. The rotation is already retrograde from the beginning. The problem is just as real. Counter-rotating eddies in protoplanetary disks are expected to be rare. The conditions that produce them are fragile. They typically do not persist long enough or remain coherent enough for a full planet to assemble inside them. Most simulations of disk dynamics do not produce planet-scale retrograde formation as a common outcome. Not impossible, not formally ruled out, but rare enough that invoking it feels like reaching for a coincidence rather than finding an explanation. The conditions required are just specific enough to feel ad hoc, chosen to produce the result rather than naturally producing it. So each of these ideas, chaotic resonance capture, primordial counter-rotation, adds something to the picture. Each also leaves something unresolved. They sit beside the four main hypotheses without displacing any of them, honest candidates in a field that has not yet found its ruling answer. There is one more layer, and it is the quietest one. It is also the one that most directly undermines the slow physics framework itself. The slow physics models, Correa and Laskar, and the work that followed, depend on the atmospheric thermal tide doing a specific job. The tide has to be strong enough and shaped correctly to push Venus's rotation toward retrograde rather than toward synchronous lock. The models know this. The simulations include it, but they can only include it as well as we understand the atmosphere. And we do not fully understand the atmosphere. The super rotation is the problem. Those clouds circling the planet roughly 60 times faster than the surface beneath them have been observed for decades. The phenomenon is real, but a complete, tested theory of why super rotation exists and why it sustains itself against friction is not fully in hand. The proposed mechanism involves atmospheric waves. Kelvin waves and Rossby waves are large-scale oscillations in an atmospheric layer, the kind of waves that also appear in Earth's atmosphere and ocean. On Venus, solar heating drives these waves, and if they preferentially carry angular momentum upward as they propagate, they could continuously feed angular momentum into the upper cloud layer, maintaining the super rotation against the friction that would otherwise drag it down to match the surface speed. That mechanism is physically plausible. Models incorporating it can reproduce something like the super rotation. But Japan's Akatsuki spacecraft, which has been observing Venus's cloud dynamics since 2015, has revealed features that the simpler models did not anticipate. Among them, large standing waves in the cloud layer that appear to be tied to surface topography. Mountains on the surface are shaping the atmosphere thousands of kilometers above them. The interaction between the solid planet and the circulating atmosphere is more intricate than the straightforward picture assumed. That discovery does not overturn anything, but it demonstrates that the atmosphere is still teaching us things we did not know. The coupling between the surface and the clouds runs deeper than expected. The mechanisms maintaining super rotation are more complex than the leading models fully capture. Here is why that matters for the whole argument. The slow physics models use the thermal tide as their engine. The thermal tide depends on how the atmosphere absorbs solar heat and how it responds. Its strength, its shape, its long-term behavior across billions of years, all of it depends on the atmospheric dynamics. And those dynamics include the superrotation. If we do not fully understand why the superrotation exists, or exactly how it is maintained, we do not fully understand the atmospheric structure that drives the thermal tide. And if we do not fully understand the thermal tide, we do not fully understand the long-term torque history. The uncertainties compound. Every layer we examine rests on another layer we have not fully read. The slow physics framework is still the most coherent and broadly supported explanation for Venus's rotation. That remains true, but it rests on an atmosphere whose most defining and dramatic feature, that 60-to-1 speed differential between clouds and surface, is not yet fully explained. The models are not wrong. They are incomplete. And incompleteness at the foundation propagates upward through every calculation built on top of it. The question of why Venus spins backward does not resolve at the level of one clean mechanism that accounts for everything. It opens into a set of interlocking uncertainties, each honest, each pointing at something we genuinely do not yet know. And the deeper we look, the more carefully we have to hold the conclusions we thought we had already secured. So that question stays open. Not just for the slow physics models, not just for the atmospheric dynamics, but for the whole problem. After every hypothesis, after every competing framework, the honest question is simply what we could ever know, and what Venus has chosen not to keep. Think about what it would actually take to reconstruct the spin history of a planet. You would want an ancient surface, one old enough to carry the marks of a different rotation rate, latitudinal climate zones, wind-eroded features baked in over billions of years, patterns that a geologist could read the way a doctor reads an X-ray. You would want a moon, or at least some orbiting body whose trajectory encodes the rotational state that existed when it formed. You would want ancient magnetized rocks, minerals that locked in the orientation of the planet's magnetic field, layer by layer as they cooled, the way a compass reading frozen in stone preserves which way north was when the rock solidified. You would want precise measurements of the atmospheric isotope ratios, sharp enough to distinguish a history of rapid, catastrophic water loss from a history of slow, gradual leakage across billions of years. And you would want a detailed map of Venus's interior, its core size, its viscosity, the strength of coupling between the liquid core and the rocky mantle above it, enough to constrain how the planet responded to tidal forces across geological time. That is the list of what we would need. Now here is what we have. The surface of Venus is too young, not slightly younger than ideal, geologically newborn. The best current estimates place the surface age below 1 billion years, possibly below 500 million. Magellan, the NASA radar mission that mapped Venus in the 1990s, produced the finest images of the Venusian surface we have ever had. And what Magellan showed, clearly, was a young surface. Volcanic plains stretching across entire hemispheres. The original crust, whatever record it held of the planet's earliest history, is gone, resurfaced, buried and overprinted and erased. A planet that keeps a diary of its past would be useful. Venus kept a diary too, but the earliest pages have been burned away, and we arrived to find only the recent entries. There are no moons. Earth has one. Mars has two. Small and misshapen, but present. Even Mercury, the innermost planet, carries a cratered ancient face that records timing and impact history. Venus has nothing in orbit. No satellite whose trajectory might encode the rotational state of the young planet. No witness, no record keeper. There is no magnetic field today, and no ancient magnetized rocks. Venus has a partially liquid iron core, but the dynamo is not running. Without active plate tectonics to cycle heat out of the interior, the thermal conditions that sustain a magnetic dynamo may simply not be present. No dynamo means no global magnetic field. No ancient magnetic field means no fossil compass readings in old rock. The geological memory that a magnetic record would have preserved does not exist. And the atmospheric isotope data we have, the measurements that might distinguish the spin histories, come from the missions of the 1970s and 1980s. Soviet Venera probes, American Pioneer Venus, Instruments built decades ago, operating in one of the most hostile environments in the solar system, surviving for minutes or hours before failing. The data they returned was extraordinary for its era. It is not precise enough for the discriminations the models now demand. Not even close. So the honest accounting looks like this. We need an ancient surface, we have a young one. We need moons. There are none. We need a magnetic record. It is absent. We need precision isotope data. What we have is approximate. The reading came back reversed. Because help is on the way. And the story of what that help can and cannot do is itself a lesson. In the early 2030s, a fleet of new missions arrives at Venus. NASA's Da Vinci, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, is a descent probe. It will drop through Venus's atmosphere from the cloud tops to the surface, sampling and analyzing the air at every altitude along the way. The isotope measurements it will return, ratios of deuterium to hydrogen, xenon, neon, argon, will be more precise than anything we have gathered before. Different histories, rapid catastrophic early water loss versus slow, gradual long-term loss, predict different isotopic signatures. Da Vinci was designed, in part, to read those signatures. It is targeted to arrive in 2031. NASA's Veritas, Venus Emissivity, Radioscience, INSAR, Topography, and Spectroscopy is an orbital mission. It will map the entire surface of Venus at high resolution, higher than anything Magellan produced. It will measure the gravity field in finer detail than we have ever had, constraining the tidal response of the planet's interior and giving the slow physics models something real to work against. It will determine surface composition through infrared spectroscopy. It will watch for active volcanism and current tectonic deformation. ESA's Envision adds complementary radar imaging, also in the early 2030s. Together, these missions will eliminate some hypotheses. They will strengthen others. They will almost certainly raise questions we have not yet thought to ask. The data will be a quantum leap beyond what we have now, and they will likely not solve the spin mystery. Not definitively. The ancient crust is gone. Veritas cannot image what no longer exists. There are no moons for any instrument to measure. The magnetic record that was never preserved cannot be recovered by a probe with better radar. Some of the evidence is not waiting to be found in a form we cannot yet read. It is simply gone. The new missions will narrow the problem. They will not close it. Some of what Venus has erased is permanently unrecoverable, and no mission we can send in the 2030s or the 2040s or the century after that will bring it back. That is not a failure of ambition or engineering. It is a fact about the planet, and sitting with that fact leads somewhere worth going. The first thing Venus tells us is how hard planetary science actually is. When multiple hypotheses can each account for every measurement we have, and yet cannot all be right, the problem is not the hypotheses. The problem is the evidence. No model of Venus's spin history is simply wrong in the way that a calculation with an arithmetic error is wrong. Each one is coherent. Each one is physically plausible. Each one accounts for the data. The trouble is that they cannot be distinguished from each other by data we currently possess. That is not a temporary gap we expect to close next decade. For some of the discriminating evidence, it is a permanent condition. The planet's own geological history has made certain questions unanswerable, and the appropriate response to that is not to argue more forcefully for a preferred hypothesis. It is to hold them all as possibilities and wait for the evidence that can actually separate them, knowing that some of that evidence may never come. The second thing Venus tells us is something about every exoplanet we have ever detected. We have found thousands of worlds orbiting other stars. For most of them, we know the orbital period, a rough estimate of the radius, sometimes the mass, sometimes a crude atmospheric spectrum if we are fortunate. We know less about them than we know about Venus, and we cannot reconstruct the history of Venus. Every exoplanet is an end state, a present configuration shaped by billions of years of impacts, resonances, atmospheric evolution, tidal talks, interactions we will never observe and may never model. We see the final chapter and we call it the whole book. The confidence we sometimes extend to distant worlds, this planet is in the habitable zone, this planet has this atmospheric feature, this planet could be like Earth, has to be tempered by what Venus teaches us. If we cannot read the history of the planet next door with all the instruments we have and 60 years of investigation, then we should be careful about how much history we claim to read in a spectrum gathered across light years. The third thing Venus tells us is about the solar system itself. The arrangement we see today, 4 rocky inner planets in stable orbits, the gas giants in an orderly procession outward, looks inevitable on a textbook diagram. It is not. It is a surviving configuration, the end state of a chaotic, turbulent, violent early history that included lost planets, shifted orbits, and reshaped rotations. The calm we observe is real, but it is also late. It was not always there, and reading the current arrangement as though it reveals the original conditions is an error. Venus's rotation is a noisy record of everything that has happened to it, across billions of years of that chaos. The arrangement it occupies today was not guaranteed. It was arrived at. The fourth thing is the deepest one. Spin is not just a property, it is a record of history. Venus's rotation, 243 days, retrograde, axis nearly inverted, is a fossil. But it is a fossil that has been written and rewritten so many times, and with its earliest layers scraped away so thoroughly by volcanism and atmospheric turnover that it may never be fully read. The comfortable assumption we often carry is that a thing's present state reveals its past. That if we measure precisely enough, if we build good enough models, we can reverse the arrow of time and reconstruct what happened. For some systems, that is true. For others, the record has been overwritten too many times. The history is still encoded in the present, but not in a form that can be uniquely decoded. Venus is one of those systems, and Venus is the planet next door, the brightest object in our night sky after the moon, studied for 60 years, with our best instruments and our most sophisticated mathematics. If this is what reconstruction looks like for a neighboring world, the universe likely contains more hidden histories than revealed ones. We will have to get used to that. And yet, 60 years of investigation have not left us where they found us. We began not knowing which way Venus rotated. We now know it rotates backward at walking pace with its axis nearly inverted, and we have 4 physically coherent hypotheses for why that might be, each constrained by real data, each falsifiable in principle by future observations. That is progress, not certainty, reduced uncertainty. The problem has deepened, not dissolved, and deepening is its own kind of advance. It means we are asking better questions than we were. The 2030s will bring more data. We will know more than we do now. We may never know everything. Venus is the planet next door. It sits closer to us than any major body except the moon. It is made of the same material as Earth, assembled at the same time, in the same neighborhood, by the same processes. And it is nothing like Earth. It spins the wrong way. It turns at a pace that barely qualifies as motion. Its surface is hidden beneath permanent clouds of sulfuric acid, its plains resurfaced by volcanism, its atmospheric history rewritten, its magnetic record absent. It is Earth's twin in composition and a stranger in almost every other respect. It sits there, visible on clear evenings just above the horizon, spinning backward, waiting, wrapped in everything it has not told us. If we cannot reconstruct the history of a planet this close, with 60 years of radar imaging and atmospheric probes and spacecraft in orbit, and the full machinery of modern planetary science, then we should hold our confidence about more distant things carefully. The universe does not owe us legibility. It does not keep its records in forms we can always read. History has a way of hiding itself, and the planets are no exception. Venus may never fully confess, but it keeps teaching us, very quietly, what it means to ask a question you cannot yet answer, and to ask it anyway,